All right. What I want to talk about now is what we've been doing specific types of. So all the left endpoint, right endpoint, midpoint rule stuff, these are all specific types of what are called Riemann sums. So we're going to go back to this general problem of, let's say, here is the area under some curve f of x on the interval from a to b. All right, we're going to do the same thing. We're going to cut this into n pieces again in the same way. All right, so just stick any old numbers in between here. The difference here is we don't need to require that these numbers be the same distance apart anymore. Right here we just say, cut this into n pieces of any size. Okay? And when we do that, we need to be able to say, well, what is the width of any interval? Right? So let me sort of say here that by cutting the interval into n pieces, we're going to have a whole bunch of intervals now. We're going to have the interval from x0 to x1, the interval from x1 to x2, from x2 to x3, and so on, all the way until the very last one, xn minus 1 to xn. All right. Now I want you to think carefully about how many intervals there are here. Right? There's n intervals because there's one for each of these pieces. So here, this is the first one, this is the second one, this is the third one, and this is the nth one. Right? And notice that this number matches with the number on the second x value. Right? Keep that in mind. Right? So what we're going to say here is that the width of the first interval, we're going to call that delta xi, right? Or sorry, delta x1. Let me move this over a little bit. So delta x1 is going to be x1 minus x0. Oops, sorry. x1 minus x0. All right. Delta x2 is going to be x2 minus x1, and so on until we get to the very last one. Delta xn will be xn minus xn minus 1. Right? So delta xi will stand for the width. Oh, I forgot the d there, didn't I? This is the width of the ith interval. Okay? Now, in each of those intervals, we have to decide how tall do we want it to be. Okay? How tall do we want the given interval to be? Okay, or sorry, the given rectangle to be. So to get the height, to get a height on each interval, what we're going to do is take a sample point, right, a sample point which we're going to call xi star, inside, or maybe I should say from each interval. From each interval, xi minus 1, xi. Right? So x1 star comes from here, x2 star comes from the second interval, x3 star will come from the third interval, and so on. Right? So we take this sample point, and then we're going to plug that into the function. Right? So what we get is that the height of the ith rectangle is going to be f of xi star. All right. So this xi star, we can pick it to be any number inside this interval, right? Any number we want. So when we were doing left endpoints, we were always picking xi star to be the number all the way on the left. When we were doing right endpoints, we were picking it to always be the number all the way on the right. When we did the midpoint rule, we would pick the number halfway between these two. Okay? So, one nice little fact here is for left endpoints, xi star, again, we started with x naught, which is a, and then we add what's actually I minus 1 delta x, right? Because in that case, delta x was always the same for each width, right? It was never different, right? For right endpoints, xi star was actually a plus I delta x, right? And that difference there is we just wanted to make sure we didn't start at a or x naught, but we actually started at x1, right? Okay. And midpoint, sorry, we would choose xi star to be a plus, it's actually I over 2 delta x. Right? So any one of these three would work out for us here. Right? Then in general here, the area, so this is just sort of an aside here. So generally speaking, right, we can pick this xi star to be anything in the interval, and then we plug it into f to get the height. So generally speaking, if we wanted to estimate the area with the Riemann sum, we would do f of x1 star delta x1 plus f of x2 star delta x2 all the way through the nth rectangle, xn star delta xn. Right, let me make that a little better there. Plus dot 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 plus f xn star delta xn. Right, and then using our sigma notation that we had, there's n pieces here. The numbers, we have kind of an index here, right? We have a 1, then a 2, then an n. So we're going to use I equals 1 to n. F of xi star delta xi. Right, this thing right here, this is what we call a Riemann sum. Right, this thing right here is sort of the most general way to write down an estimate for the area. Now, one thing we want to point out here is that this estimate improves as n gets larger. In other words, as n goes to infinity. Right? So we'll talk more about that in a later video. Right? But what I wanted to do now is I want to turn to Mathematica and look at how we can use Mathematica to compute these Riemann sums, at least in the case of the left, right, and midpoint rules. And we want to do it in a simpler way, right? Where we just sort of like program in certain information and get it from there. So let's switch over. So what I've done here is I've written out code with a bunch of explanation, right? So here we're going to clear out all these symbols, right? Now I'm using k for the index instead of I here in the Mathematica code, right? So here the first thing we have to do is define our function. So our function here is f of x. Then the next thing I'm going to do is we want to say, well, what is the starting point and the ending point? What is the A and the B value? What interval are we finding this area over? Okay. And then we want to specify, well, how many rectangles do we want to use? Okay. And here, when we're doing Riemann sums with the left endpoint, right endpoint, or midpoint rules, we're taking our intervals to have an equal width. Each interval has equal width. So to compute that number, delta x, we just do b minus a over n. Okay. Now this here, this is actually our xi stars. Again, here for Mathematica, we've called this k. But these are the xi stars right here. Okay. And right now it's set up to be left endpoints. But if we wanted right endpoints, we could just delete this and make it a k. Right? If we wanted midpoints, we would change this to a k over 2 here. Right? So it's just, adjust as needed. So I'll switch this back to left endpoints. Okay? And then finally, we want to add all these up. So here, to do a sum in Mathematica, we write the command sum. Here, this stuff is the stuff that we're trying to add up. Right? These are the things we want to add together. So this would be, fxi star times delta xi, right? Or in this case, just delta x, because they're all the same. And here, this is the number that would go on the bottom of the sigma. This is the number that would go on the top. Right? There is a command in the basic math assistant that you can look for as well that will pop up a sum like this. And you could also type in the same kind of thing here. So k equals 1 to n of f of p of k delta x, right? And you could see, so this is the same thing as this, right? So in Mathematica, you can use the sum. I'm more of a fan of just sort of like typing text out, but completely up to you how you want to use it. All right. And then below here, I've included a version of that code without all the comments. So this is just sort of telling you how to use each piece of it, what each piece of it's doing. Down here, I've just kind of cleared all that out. Right. So what's the nice part here? So let's run this. Right now, this goes back and computes that very first example we did. Right? So we get a 10. So let's say, maybe we wanted to do an example. We wanted to estimate this area, but with 50 rectangles, right? So that would be doing this here. That'd be finding this estimate right here. So if we do that, so just change the n to a 50 and run that. Boom. Now, it might be useful if you want to get a numerical estimate. You could add an additional line here just to give a numerical estimate out, right? Or a decimal approximation anyway. And so this n here will just take an actual fraction expression and turn it into a decimal. All right, and there we go. We see the 10.66, right? Which is basically 10 2/3. All right. Yeah, so this code here, it can help you sort of, instead of having to do, writing out all the numbers and adding them all up and doing all that, for doing stuff with like 4 rectangles, it's pretty useful to do that by hand to kind of understand what's going on. But if you want like a real actual estimate where you're using 50 or 100 or, like 1,000 rectangles maybe, I doubt you really want to do all that work by hand, right? And, here we can actually see it happen. All right. So in the next video, we'll see how do we take this process and turn it into the true area of the function. All right. Have a nice day.